All right, today we're going to calculate net work of a system. So just a practice problem that we'll do in class, and then I'll define the first law, and then we'll do like a little problem on heat transfer, I think. So total power, net power is kind of that's what that's called too. Bless you. So while you're writing it down, I'll start doing the givens. So we're doing this practice problem, Ben. So keywords. What do you think some keywords are? Constant torque. Okay, that's easy because there's no integral for that. So we have electric power. Then we have a load. We have a shaft spinning. So what type of work? What type of work or power do we have? Shaft and electric, right? Okay. Which one has to be higher? Why? The efficiencies, and we'll talk about that here next week. Okay. Yeah. All right. Everyone got the problem? Ben, I can give that to you. All right. So here are the givens. Oh, okay. So n dot we'll call revolutions per minute. So 955. We have a torque. We have the electric power, 2.0 kilowatts. If you are, and I've had some students come in, but if you're having issues with units or other things, let me know. Okay, I can help you with stuff in your notes or during office hours. So I drew, it's kind of a tiny motor and shaft, but we have electric coming in and we have shaft. What we want to do on this sketch is we want to do a boundary and label what's coming in and what goes out. So what's coming into that boundary? Well, yes. And then what leaves? Exactly, work of the shaft or power of the shaft. Yep. What also leaves that I'm not going to put on there? Heat. Yep. So the net power, or that total power, we have W dot net equals W dot in minus W dot out. And we do in minus out so we can get a positive value. Okay. Am I okay if I scroll here? Does everyone have? I think most people have that. Now I'm doing this. I know it's step by step, but please do that because trust me. And you have no idea when we start doing stuff later on how important these steps are. So I labeled each one, electric and shaft, and we already have the electric power, which is 2.0 kilowatts times 1,000 watts and 1 kilowatt. And then what's the shaft power equation? Remember? Yep. So, oops. I kind of skipped a step, but I'll just do this. And then I'll rewrite it down below. Yeah, I can. Do you want me to? Yeah. Sure. Here, I'll erase this then. Well, we already have it, but that's fine. Electric is voltage times current. Okay. Yep. Thank you. I never thought about doing it that way. And then I'm going to just convert in thin air just real quick. Okay, so minus, I'll put brackets, 2 pi 955 revolutions per minute. Got to convert that to seconds. Yes. Oh yeah, what did I do? No, divide by 60. Revolutions per minute. So the minutes are on the bottom. So 1 minute, 60 seconds. See, if you don't show me this, then you're going to be confused. If you do this, this is the way I do it. So much easier. I still do it to this day. Even if I have to do a conversion, I still do it like that. And then 18. And I think the result comes out to be 200 watts. And boxer answer. So the first law of thermo. I'm going to show you, and then we're kind of basically, in the homework problem, is going to be basic concepts. We're not going to dive deep. Here, it kind of will show you where it comes from. So the fundamental equation, and I'll write these words and then we'll write an equation. So the basic fundamental is the energy coming in. You can think of a boundary, through the boundary, or out of the boundary, is really the change in energy of the system. So if we take this room as our system, we have people in here, and each one of us is giving off heat, right? We have light bulbs that are on. We have the projector that's on. Computers, they're all giving out heat. All right? If yes, we'll do a practice problem on that coming up. Yep. Okay. But we're all giving off heat. We're all supplying stuff to this system, this room. Okay, and it changes the energy. That's the bottom line. But what we're going to do is we're going to look at each case on the left and on the right. So let's look on the right, which is the change in energy of the system. So delta E of the system. Beep. So this room, think of it as a ball, or you think of a ball on a hill. What energy change can a ball have? Yeah, which is kinetic for movement and potential for elevation, okay? I'm going to just leave the first one empty. So change in KE plus change in PE. What else can a ball do from winter to summer? Okay, yeah, that's a good point. Yep. All right, I asked it weird. It can change temperature, okay? I probably should have said this room. Yeah, never mind. Okay. Sometimes on the fly it doesn't work too well. But yeah, you are all right. But it can change temperature, which is internal energy. Where is V? U, delta U, delta U. Big U. If I divide each one by mass, what do they all become? What was that? No, that's if there was no heat, that's energy. But if I divide each term by a mass, by kilograms, each term now becomes a specific value per unit kilogram, okay? So delta big U is M U2 minus U1. And again, I'll rewrite these. I know we did them, but it's important to have them again. V2 squared minus V1 squared. And delta PE is mg Z2 minus Z1. So the system is the system. It could be this room, it could be a ball. All right. Typically for us, we're not going to look at like solids like a ball. Okay. Majority of the time, we're going to look at systems that are stationary. So this room is stationary. Is it moving? No. Is it changing elevation? The whole system moving up and down? No. So typically, we're not going to deal with any of that. Okay. Okay. That is above my pay grade. Okay. So typically, we will always, the majority of the time, neglect those when we start dealing with our systems. Okay. So the system, though, could change temperature, which changes internal energy. So remember that. All right. Questions on this system? Now let's look at the other side of the equation. What can come in and go out? Well, we've already talked about this kind of briefly. So E in and E out. There's three forms. What are the forms? What's shaft? Electric. Force times the distance. They're all work. So the first one is work. What else can we have go through a boundary? What's coming through here? Heat, which is? Yeah, heat, yeah. Yep. I thought you said sun, which is heat, but I was thinking sun. So yeah, heat. And then if we open this door, we have what coming in? Air, which is mass, which is what did I call it here? Mass flow, right? So those three things can come in and out of the boundary. All right? So is there an outlet anywhere? Is that mass flow, yeah, we'll get to that. Mass flow is only for open, yeah. So here's an outlet here. When I plug a power in here, we have electric coming in, which is work to the boundary, this room. Okay? What happens when you plug in something like a heater? It's electric power, but that converted to thermal energy, which is internal energy. So when you plug a heater in your room, okay, you have electric power coming in, and it actually does what to the room? It increases the temperature, which increases the internal energy. Okay, does that make sense? Right. So let's write this. So E in minus E out equals Q in minus Q out, because we're looking at net values. W in minus W out, and plus E of the mass in minus E of the mass out. To identify them as work, not watts. Okay. let's see if you remember. If Q is 0, what do we call that? Insulated. And the other engineering term, it is in what type of system? Keep guessing.
Adiabatic?
Adiabatic. That's what I was looking for. Adiabatic. Yep, adiabatic. It's insulated. Okay. If W is 0, that means there's no work. There's no mechanical work. What's that? Insulated. Insulted. Oh.
I was like, what's insulted?
What did I miss here? Where is it? The A?
Yeah.
It's insulted. I'm going to see that on the assumptions, right?
You're insulted.
I'm insulted. I guess so. Oh, man. I do these on purpose. You know that, right? If the net of E mass is 0, what type of system do we have? Closed. So much easier to work with, trust me. Okay, now we're going to combine all these to get you one long equation. Okay? So, I'm going to rewrite this. E in minus E out equals delta E of the system. We'll do this once, and then you can kind of write the final equation here. All right, so we have, let me do this. Q in minus Q out plus W in minus W out plus E mass in minus E mass out equals delta U plus delta PE. Oh, I'll do KE first. I think that's what I did before. Okay, I'll do it one more time. And I'll do QI minus QO, just abbreviate. You already have this, but it's nice to know, okay, here's the complete full-on equation. M U2 minus U1 over, oh, no, not yet. I jumped the gun. We'll lay out each term coming through the boundaries and what's happening to the system. Okay? We can do one thing to this. We can divide each term, or the whole thing, by dt. What's that going to give us? It'll give us rates, right? What does m over dt get? What does that give us? So much mass per unit time gives us mass flow rate. Okay, so last time I promise. Okay, so we get Q dot E minus Q dot O. Yep, by delta T, some amount of time.
Oh, okay.
I promise you this is the last time. We're going to elaborate when we get to like chapter 4 or 5 with the mass one. Okay? And we're not going to do the notes. I have a PowerPoint that does it because it's so long. what I do for that. I know, right? It's already week 2, day 3, and we're doing all this. Oh, I got it in barely. Oh, yep. Typically, we don't worry about those for the system because we're going to assume it's a stationary system. All right, so here is a sketch. Just a crude problem. Don't overcomplicate things. We have Q dot of the window. We have Q dot of the people. We have Q dot of the light bulbs. And we have Q dot of the air conditioner, we'll call it cooling. Given. Yep, that's the air conditioner. I'll talk about that. Oh. Oh, I might as well draw the boundary for you. So in this problem, we have a house, and we want to know how many air conditioners we need to keep the temperature at 21 degrees C. So what's being supplied in? Well, we have 40 people, that's what Q dot P is, 40 people, and each person gives off 360 kilojoules per hour of heat. We have 10 light bulbs, and each one of those gives off 100 watts. Q dot of the W is like the window isn't very insulated, so we have that much heat coming in through the window, okay? And that is per air conditioner how much they can cool, so 5 kilowatts. Assumptions. Is this system moving? No. So the system potential and system kinetic are 0. What else? What else can we assume? Is the temperature changing? No. So what is delta U? 0. There's no change in internal energy. And if I say all the energy coming in must equal the energy going out, that means that there's no steady state. Yep. And so SS means steady state. And that means the change in energy per unit time, or E dot delta E dot of the system is 0. So the system is not increasing energy throughout time. Because whatever comes in must equal what goes out. Actually, we can add one more. Is there any mechanical work, mechanical objects doing work? No. No work. So what is really, it's all due to heat, right? So in your first law, you should have no work. Is it a closed system? It is, right? We could actually add that too. Look at that. I didn't do that. So there's no E of the mass, no fluid coming in and out. All right. Which is a little weird, right? If you think about it, it's a closed system, but we have air kind of transferring, right? But it's, I don't know, we'll just do this for right now, okay? With the air conditioner, it cools. Well, you're not really, the air conditioner is not really taking air, it's cooling the air by the inside component. So it is still a closed system, all right? All right, so let's write the solution. Yeah, there's nothing open. So on your solution, make a heading for me. So first law. And we're dealing with rates. So I want you to start with either the rate 3, what I'm going to show you here, or the work one, or the energy one, sorry. And then write out the steps here. So we know that this is 0 because it's steady state. So Q dot in minus Q dot out plus W dot in minus W dot out plus E dot mass in minus E dot mass out. Then we can eliminate. Those are garbage, those are garbage. And we just have what's coming in must be equal what goes out. So 0, what's coming in? Q dot of the window plus Q dot of the people plus Q dot of the bulbs minus Q dot of the cooling. Because in reality, we need to figure out how much energy we need to take out, right? The cooling, and then figure out based on that and size the air conditioners. So I'm going to rearrange, which is easy, right? I do easy ones sometimes. Sometimes I'll do hard ones. We'll get to there. And let me plug the numbers because this is a little weird units, right? I did that on purpose. So 15,000 kilojoules per hour. Is that right? 15,000? Oh yeah, per hour. We need to convert that 600 seconds. What's that? For the cooling? Or no, for the window? No, the window I think I wrote 15,000 kilojoules per hour, right? Yeah. Yeah. People. We had 40 people times 360 kilojoules per hour again. 360, yep. Convert that. 1 hour, 360 seconds. Plus, we had 10 light bulbs times 100 watts. And what is a watt? A joule per second. Yes, so joule per second. and let's convert that to kilojoules. So what do we have to do? Divide by 1,000, right? Because you want the joules on the bottom to cancel. 1 kilojoule. Okay. And when you get this, and double check this for me, did I get 9.17 kilowatts, which is also 9.17 kilojoule per second. Is that right? Anybody check it? Is there? Okay. All right, you believe me? Then how do we find the number of ACs? Yeah, just Q dot cooling over the Q dot of the AC. Number. And we get 9.17 divided by 5 kilowatts. And we get 2. We need 2. Hit the round. 2. It's a little bit more, but you can adjust what you need. You can't do it with 1. There's no physical way. It doesn't take that. You need more.